Okay, up until now, we've said that stoichiometry does not matter necessarily for the rate law or the reaction order because that doesn't tell us about mechanism. So, but now let's talk about mechanism. So what we want to do is, for a mechanism, remember for organic chemistry, you're pushing around arrows. So these are little steps that tell us how the reaction proceeds through our different intermediates and transition states. So each of those arrow pushing previously are what's called elementary steps. So what this means is that for each of these elementary steps, for each step of the whole mechanism, suppose we're going from, like, let's say A goes to B, and then that goes to like 2 equivalents of C, and that goes to D. So our overall reaction stoichiometry is going from A to D. So that stoichiometry might not matter for our elementary steps, for our rate law. But then if we break it down into a mechanism, if each of these elementary steps, so 4 elementary steps, then the stoichiometry of each elementary step gives us the reaction order. Stoichiometry gives us reaction order. Oop. So obviously, your mechanism would have to be correct, right? So a mechanism, okay, this is kind of dogma. Mechanisms can't be proven, only disproven. So what this means is that a reaction proceeds, what we know is a reaction proceeds from reactants to products. So this is what we know. And then for this reaction, these are what you propose. So you're proposing, these steps, proposals, right? These are proposed mechanistic steps. And then so from this proposal, then what we want to do is we can use each elementary step, assign, let's say, reaction constants K1, K2, K3. And then from that, we can derive what we expect our rate law to be. And then if our data, our measured data, like our concentration over time, don't match that predicted rate law, we can disprove a certain mechanism. And then you have to go back to the drawing board and then propose a different mechanism. So for these elementary steps, what I mean by that stoichiometry determines reaction order is that for our first step here, we could then say that negative dA over dt is just, so this would be a first order reaction equals K1 times A. And then because this coefficient is 1A goes to 1B, negative dA dt equals K1A to the 1. So that's because of this guy. So that's why this is first order. For our second step then, for the formation of B and the consumption of B, so now for B we have 2 elementary steps, one going to B, one going away from B. So then what we can say is that dB dt equals K1A, because that's the formation of A, or formation of B rather. And then we're losing B in this consumption step, so that would be K2 times B. And then so that's dB dt. And then so, but whether we can know these concentrations over time or not depends. We'll go over an example of that in the next video. So that's our first order reaction. Okay, first order reaction. And then this second reaction here is a little bit more complicated, right? So we know our reaction rate, which will be 1, 2 dC dt equals, and then that will be K2 B, right? This will be the formation of C. And then this is going to be, and then we lose C. And then so because this coefficient here is a 2, this elementary step would be a second order reaction. And then this would be minus K3 C squared. So again, this is a 2 because there's a 2 over here. So et cetera, et cetera. This is how we can turn elementary steps and a proposed mechanism into rate law. So then we have to do a bunch of integration or something like that, or calculation to figure out what our final model should be. In practice, sometimes you use software or other computational things to kind of help you figure out what your observed rate law should overall be. OK, let's do one cool example. Suppose we have a reaction equilibrium. Let me do this up here, or actually over here. So let's suppose we have some sort of equilibrium reaction. So for equilibrium, what we're saying is that if A is in equilibrium with B, there's a forward reaction with some rate constant K1. And then what this means for them to be in equilibrium, this would B would convert back to A in some reverse rate constant K minus 1. So in this case, using this same kind of process, we have one forward reaction, first order, where A goes away. So dA dt equals this first step where A goes away. But then the second reaction where B in a first order reaction goes back to A. So this would be formation of A. So this would be plus K minus 1 B. And then so this is the rate expression for A over time. So at equilibrium, by the definition of equilibrium, we know that we're not accumulating or losing any A, right? The dA dt equals 0. So what this means is that we can then rearrange terms, and what we get out is that B over A equals K1 over K minus 1. And then, so again, this is the forward reaction rate constant divided by the reverse reaction rate constant. And then what this term is, cool enough, is products over reactants of this equilibrium expression. So this means that our equilibrium constant, big K, equals the forward reaction rate constant divided by the reverse reaction rate constant. So here we related thermodynamics, equilibrium constant, to kinetics, reaction rate constants. So I thought this was a cool example of using elementary steps and figuring out rate law to get to some other final expression that we want.